We're the Michigan Mars Rover team, and we're proud to introduce you to our 2023 Rover. We learned a lot at competition last year, and our team of over 100 members is working to implement these lessons to build our best Rover yet.
Our Rover builds upon successful components of past Rovers, while improving identified failure points. We've iterated upon our welded aluminum chassis with the Rocker suspension, and have improved our custom drive gearboxes to optimize mass. Our 3D printed wheels have been tested and iterated to improve traction. This allows the Rover to maneuver through a rock garden and climb slopes up to 45 degrees. We've upgraded our 6-degree of freedom robotic arm to use brushless motors with our cyclotal gearboxes. These gearboxes have been redesigned this year to work with these new motors and optimize strength and control, allowing the arm to easily carry loads up to 10 kilograms. The end effector is capable of performing precise servicing procedures and grasping objects up to 5 inches wide. Our wrist now uses a slip ring for wire management, allowing for infinite rotation and ease of operation. In addition, inverse kinematics allows the operator to quickly move the end effector to a precise orientation and position.
This year, we have built a separate sample acquisition arm to efficiently pick up soil and observe both rock and soil samples. This arm has 3 degrees of freedom and is able to precisely maneuver a scoop, microscope, and high-resolution camera for rock investigation. We have 2 deposit points for soil. One is at our science carousel, which rotates to provide a separate set of tests for each of 3 samples. The other deposit site leads to our sample cache and custom Raman spectrometer, where one sample of particular interest will be deposited. Our sample cache closes securely with a gear mechanism and can easily be removed to hand to the judges. Within the science carousel, chemical tests are observed through cameras and sensors to search for signs of amino acids, chlorophyll, and lipids. Additionally, our custom Raman spectrometer analyzes soil for kerogen and carotenoids. Between the sample acquisition arm and science carousel, our rover can efficiently analyze up to 3 soil samples and 9 rocks for the science mission.
Our electrical system has been upgraded with a focus on accessibility and efficiency. We have designed custom brushed motor controllers to seamlessly fit in with other systems. An MCU board combines control of science systems and all brushed motors on board the rover. In addition, we have also made STM32 development boards, which allow systems to be integrated off-rover. Custom converters and a fuse board power onboard devices with protection from overcurrent. Our new brushless motor controllers are mounted on the robotic arm, which simplifies wiring and enables the use of both relative and absolute encoders. A 36-volt battery provides more than 2.5 hours of continuous operation, and an accessible push-button e-stop allows us to shut off the rover at a moment's notice. Our communication system utilizes 900 megahertz and 2.4 gigahertz to maximize both range and data throughput from the rover. Through our testing, we have determined the optimal system for each mission's challenges of no line of sight or elevation changes.
We've overhauled our autonomous navigation system into a microservice architecture built on Robot Operating System. We've also implemented an extensive regression testing protocol against the gazebo simulation environment. A Z stereo camera is used for detecting and estimating the pose of AR tags, while a localization microservice keeps track of the rover's absolute pose by fusing IMU and real-time kinematic GPS data in an extended Kalman filter. We maintain an additional localization frame, computed using visual odometry, that is locally accurate for situations such as driving through the gate. Perception and odometry information is processed in a state machine to make navigation decisions and complete the autonomy mission. The navigation state machine now includes various failure recovery mechanisms, including backtracking when sensor signatures indicate an obstruction.
This year, we again focused on early integration and testing to ensure robust designs. We have continued to use development boards to separate our core rover systems for testing in parallel. Additionally, we have been able to use last year's rover, Rosie, to test our autonomous navigation system. We are prioritizing mock missions and operator practice again this year to develop and optimize competition strategy. We use our mock lander as well as our university's robot playground and Mars Yard to test our rover in URC-like conditions. We are excited to show you our new rover and confident in our ability to succeed at the 2023 University Rover Challenge. Thank you for your consideration.
Go!